second back pocket.
Alright, say it again.
It's always an odd thing to find an open bag of food in your second pocket. Pretzels they may be, but still.
Yeah. If you're my son, it's not that unusual.
Well, I had anorexia, so I'm not prone to eating things. Which makes it all the more ironically funny, if you will. Yeah?
I never do have pencils anymore.
Do you want one like this? Do you want...
Honestly, anything.
Okay, well I'll give you one of the ones that don't fall apart.
Thank you.
Alright.
I have 3 super erasers if you want one of those too, because that one is not trustworthy.
Ron won't make a mistake. Right?
What?
You won't make a mistake. You don't need an eraser.
Oh, no. I never make mistakes. I only make jokes.
We're so just, we juxtapose each other so well.
Any questions? What about now?
Do we have any questions?
Alright, so the last thing we did, I know we were doing centripetal motion. Did we do car going around the banked curve?
No.
Alright, we should be good there.
I think we started it.
We did ideal. Okay, thanks. Alright, so we did an ideal, we didn't actually do it.
Just like, I want to do some physical.
Alright, so I assume the radius, 100 meters is what I usually use.
Yeah.
What was the angle?
We don't know the angle.
I did not get the angle. Okay.
What was the, did we end up?
20.
Yeah, I think, yeah, you eventually give it to us. Today's.
And we ended up with this ideal speed is the square root of GR tan theta. Is that right?
Yeah.
Okay. So that would be the speed you would take in order to be able to take that curve without sliding up or down. So given the 20-degree angle, given that we're on Earth and the R is 100 meters, what was that speed? I assume we did a calculation there.
Yeah, 18.886 meters per second.
18.88?
18.886, so it would be 18 point, yeah.
When you write overhead, you mean bird's eye view?
Yes.
We did this on Thursday. Yeah. No, actually,
That's
funny, I'm like just.
All right, so now we have, I want to figure out what is the maximum speed so you don't slide up the ramp.
Yeah.
Given a 20-degree angle right now. So we start out where we always do.
Yeah.
Morse diagram.
Yeah.
So this is frictionless. And let's put in mu, so S is, I think it's 0.7 for rubber on asphalt, somewhere around there. Car.
Gravity is still on Earth.
Yep. Earth 1. the international fans out there, when I say the original, I'm not for the Earth expansionists. We're still assuming that the current acceleration of gravity is valid. There are certain beliefs that the Earth is actually expanding, that continental drift. The plate tectonics is not the real explanation for why the continents have drifted, but the Earth used to be smaller and it's slowly getting larger.
An argument
as it
could be
spins.
made for the same thing, that it's shrinking.
Is there
I had not heard the Earth shrinking, but
Is there not one while
When,
Earth is gone?
what day did we do this? When did we do this and what day?
Thursday? That was Thursday.
or Wednesday.
No, it wasn't Thursday, cause we were all working on the lab, well, after class, so
I thought-
Wednesday.
I thought Wednesday we worked on the master set.
Yeah, it's been last Tuesday then.
That was.
Is there a video of this?
Yeah, at this point, all the videos are loaded.
Okay.
Oh yeah, someone's right.
All right, so the forces, we're doing the force diagram. I have my beautiful picture of a representation of the car. What are the forces acting on the car?
Well, there is weight, force of gravity, there is normal, and that is all.
Friction.
No, it's frictionless.
Oh, we're dealing with friction. This
Yeah, I
this
gonna
was
say
the
we just
frictionless
did
bit.
mu,
Oh,
so-
sorry.
Friction, continue.
Acting which way? We're trying to find the maximum speed so we don't slip.
Wouldn't it be going counterclockwise?
We don't want to slide up or down. We assume that
It's going in a circle.
in the direction that it is going, that there's no slipping there. We're worried about slipping up the ramp.
Oh,
So the friction is down.
Yep, friction would be down. Well, down and
Down the
to the
ramp.
left, given this.
down the ramp.
Yes.
The ramp.
Force diagram, direction of acceleration. Stephanie, I wasn't quite sure whether you were indicating your answer or not.
Like, acceleration is going this way,
Or not.
or not,
Rookie mistake.
this way?
Even worse.
Oh, where's, that makes, oh, acceleration's going this way?
Towards the center of.
Or that, this way?
Yeah,
'cause it's
towards the
this
center
way?
of the circle.
Sorry.
This is centripetal motion, chapter 6. It's traveling in a horizontal circle.
This way.
My acceleration is in that direction. I'm not drawing that arrow on my diagram. I'm just drawing it off to the side because it is not a force. So what do I need to break up? Oh, coordinate system.
That way can be I, and then that way can be J.
Is that a
Oh, we
K?
could do that. Sure.
Okay, whoa,
You're gonna
so
quadruple
is
the
it?
amount of math we have to do.
No, J is with weight.
You got JV down?
Yeah, and then I is direction of acceleration.
Oh.
Trust me, guys.
If you had done it this way, if you had done it parallel to the ramp and perpendicular to the ramp, then we have two accelerations to deal with. And so we need another equation, which would be that the actual acceleration is the square root of those components squared, the sum of it, the square of those components.
Will we have to do any of that on the test? The final test, is there one?
Do, what do you have to do it the hard way?
Yeah.
No, it's your choice.
Thank God.
It depends on whether you. Sorry.
All right,
Sorry.
what are we breaking up?
Well, normal force and friction.
Yeah. Now, if we had done it the other way with the other coordinate system, we only have to break weight up. We've done that enough. That would be simple. So we would save time, a little bit of time in the breaking up of components. However, when we actually do the solving, it's gonna spend much more time. And I do a video with choosing coordinate system like that as opposed to like that. And I actually should time it, or at least hit the marks. But I go through that exercise in one of my videos.
What the heck?
All right, so if we break y up, well, let's see, I have some angle theta there. I have y going like this and breaking it up into horizontal and vertical components. Well, that's a skinny angle there, that's a skinny angle there, so that's gonna be theta. Therefore, this would be y sine of theta. So I end up with y sine of theta, y cosine of theta. I have weight acting down. Excuse me. And then friction, we need to break up also. And in some senses, breaking up friction would have been easier to do first, but I know friction is going down and to the left. So I'm gonna have a component that's down and a component that's to the left. I know that since it is perpendicular to the normal force, the trig functions will swap. So this will be f cosine of theta, and down will be f sine of theta. Now, if you're not comfortable with that way of doing the analysis, I also have friction is acting down the ramp. I'm breaking it up into vertical and horizontal components. I've already given you that angle as theta. My opposite side is sine. The adjacent horizontal side there is cosine.
Could you repeat that but slower? The first method
Break
specifically?
up the first method?
Yeah, could you explain it a
Oh,
little
yeah.
bit?
I try to draw it more realistically, or at least draw it more extremely. I'm gonna make theta, I'm gonna pretend theta is a small angle. Normal force is perpendicular to that.
Okay,
And I'm gonna break it up into horizontal and vertical components. So I have a component going to the left and a component going up.
okay,
I know one of the angles is theta. That is a skinny angle there,
okay,
so the skinny angle here would also be theta.
yes. Now what about that little angle underneath the horizontal arrow?
This angle down here,
Yeah,
that is also theta.
does that matter in this problem?
Well, it depends on how you want to figure out which of, in my triangle here, in this right triangle, trying to figure out which angle is theta. If I were not trying to do it visually and trying to do it using geometry, then I would establish if that angle is theta, that angle is theta.
Okay,
That's a right angle, so this angle here must be the complement of theta. That's a right angle, therefore this angle must be theta.
okay, thank you.
Other questions?
And then could you explain how you got the trigonomic functions from that?
Once we establish, this is our triangle here, this is my normal force, is my hypotenuse. This angle here is
So
theta.
it's not the upper arrow? I thought it was the arrow that, it was relative to the arrow that points up.
Oh, that one right there?
Yeah, the theta.
Whatever I'm breaking up is,
So it's the side and not the angle.
it's the side and not the angle.
Cause,
Whatever I'm breaking up is the hypotenuse. I'm breaking normal
Okay.
force up, so it is the hypotenuse.
okay,
Other
So-
questions? Robin? Oh, I thought you were about to ask another question.
I was, and then you called me and I lost my train of thought.
Okay. Well, when you think of it, 2 in the morning.
Okay.
Will do. The slope is friction?
The friction is acting down in that direction.
Okay, so how did you get F cosine theta?
When I have perpendicular vectors, such as normal force and friction are perpendicular to each other,
Yes.
then I
Oh,
know
we're-
that.
We're changing this as if it were like this. rather than this.
Yeah.
Then follow the hand gestures there.
So, in the graph with the box and the YWF whatnot,
Yep,
it's like, this is the Y-axis, this is the X-axis.
the,
Y-axis, sorry, normal force axis and friction axis,
if you wanna look at it that way.
okay. And then you're just tilting that so it's easier on that problem?
No, not tilting it at all. I have, let's see,
Then how is friction going left horizontally and not left downwards?
there's a downward component and a leftward component. Friction's acting down the ramp. Cause I'm trying to find the maximum speed.
Okay, thank you.
Yep. Other questions while Moran is fixing her blanket? I guess you dropped something?
Yeah, I was just dropping stuff. Thank you.
Next step, equations of motion.
Yes.
This is my favorite part.
Is F sine theta the same as weight in this case? Cause they're both pointing down.
No, they are two separate
Okay.
forces downwards.
Okay.
So, I hat is friction cosine theta plus normal sine theta equals mass times acceleration. Would the acceleration be centripetal?
It would indeed.
Okay, I just wanted to clarify. And then j hat would be normal cosine theta minus weight minus friction sine theta equals.
You've already forgotten what Ava said.
Wait, what did I do? Minus.
Now, if you had written that down, you would have gotten the exact same answer. That's not going to affect the final answer.
Okay.
It's a process issue.
Oh, sorry. Yeah, I put it out. Okay, I lied. It's weight plus friction sine theta minus normal cosine theta. Okay. And then, equals 0. And now we do substitution.
Okay.
Which is F cosine theta plus y sine theta equals mass times velocity squared over radius without a
Okay.
question mark. And then j hat would be weight plus friction sine theta equals y cosine theta, and then the weight is mg
Wait.
equals y cosine theta.
I got some blanks up here. Why?
Cause we didn't account for gravity yet?
No, that's not the issue. We're in the substitution phase.
Friction can be normal force times mu.
Yeah.
Which mu?
Static.
All right.
This class.
So mu s y cosine theta
Yeah.
and mu s y. All right.
Wait, why cosine theta?
Y cosine theta there?
Yeah.
Cosine theta there?
Oh.
I wasn't sure, Moran, if you were planning to do substitution in two parts or whether you're just always taking on the friction.
Sometimes I just do a second version of substitution for no reason.
Now, if we look at our unknowns, I don't know why. I don't know what the normal force is, in other words. I don't know the speed. I don't know mass either. But turns out, don't care about the mass. But assuming the mass will cancel out, I have v and I have y, I have two unknowns, two equations. How do you solve it?
Could you let me finish writing this down and then repeat that?
So we don't know y and we don't know v.
Correct.
Why don't we know v again?
That's what we're trying to find.
Um,
That 18.886 meters per second is, if it were frictionless, what's that ideal speed to take it? We now added friction. Trying to find the maximum speed so we don't slide, so we're going above that. Which is a quick and dirty check, is whatever answer we get, it better be bigger than 18.886. So the question is, how do we solve it?
um,
Oh,
no.
I thought I figured it out.
By any chance, do we need to use like? No, we don't have time. Do we need to use 2 pi r anywhere in this equation?
No.
Okay. Then I'm not.
Alright, first, let me make, we have to get rid of the mass somehow. Mass has to cancel out. So, if I just solve for mass in one equation and plug into the other, now I have one equation, two unknowns. Which is very difficult to solve, unless something cancels out. Which, actually, it would, but